Alpha Centauri. Alpha Centauri, abbreviated Alpha Cen. Alpha Cen is a star system in the Orion Arm of the Milky Way galaxy, and is the closest star system to the Solar System, being 4.37 light-years, 1.34%, from the Sun. It consists of 3 stars. The pair are Alpha Centauri A, also named Rigil Kentaurus, and Alpha Centauri B, together with a small and faint red dwarf, Alpha Centauri C, also named Proxima Centauri, that may be gravitationally bound to the other two. To the unaided eye, the two main components appear as a single point of light with an apparent visual magnitude of -0.27, forming the brightest star in the southern constellation of Centaurus and the third brightest star in the night sky, outshone only by Sirius and Canopus. Alpha Centauri A, Alpha Cen A, has 1.1 times the mass and 1.519 times the luminosity of the Sun, while Alpha Centauri B, Alpha Cen B, is smaller and cooler, at 0.907 times the Sun's mass and 0.445 times its visual luminosity. During the pair's 79.91-year orbit about a common center, the distance between them varies from about that between Pluto and the Sun to that between Saturn and the Sun. Proxima Centauri, Alpha Cen C, is at the slightly smaller distance of 4.24 light-years, 1.30%, from the Sun, making it the closest star to the Sun, even though it is not visible to the naked eye. The separation of Proxima from Alpha Centauri AB is about 15,000 astronomical units, 0.24 light-years, 0.07 pc, equivalent to 500 times the size of Neptune's orbit. Proxima Centauri B, an Earth-sized exoplanet in the habitable zone of Proxima Centauri, has been detected and may be a destination of future interstellar spacecraft, including a fleet of Starship spacecraft currently being developed for a flyby mission by the Breakthrough Starshot project. Nomenclature: Alpha Centauri, Latinized to Alpha Centauri, is the system's Bayer designation. It bore the traditional name Rigil Kentaurus, which is a Latinization of the Arabic name Rigil Kentaurus, meaning foot of the centaur. Alpha Centauri C was discovered in 1915 by the Scottish astronomer Robert Innes, director of the Union Observatory in Johannesburg, South Africa, who suggested that it be named Proxima Centauri. Actually Proxima Centaurus. The name is from Latin, meaning nearest star of Centauruses. In 2016, the International Astronomical Union organized a working group on star names, WGSN, to catalogue and standardize proper names for stars. The WGSN states that in the case of multiple stars the name should be understood to be attributed to the brightest component by visual brightness. The WGSN approved the name Proxima Centauri for Alpha Centauri C on 21 August 2016 and the name Rigil Kentaurus for Alpha Centauri A on 6 November 2016. They are now both so entered in the IAU catalogue of star names. Nature and components. Alpha Centauri is the name given to what appears as a single star to the naked eye and the brightest star in the southern constellation of Centaurus, at -0.27 apparent visual magnitude, calculated from A and B magnitudes. It is fainter only than Sirius and Canopus. The next brightest star in the night sky is Arcturus. Alpha Centauri is a multiple star system, with its two main stars being Alpha Centauri A, Alpha Cen A, and Alpha Centauri B, Alpha Cen B, usually defined to identify them as the different components of the binary Alpha Cen AB. A third companion, Proxima Centauri, or Proxima or Alpha Cen C, has a distance much greater than the observed separation between stars A and B and is probably gravitationally associated with the AB system. As viewed from Earth, it is located at an angular separation of 2.2 degrees from the two main stars. Proxima Centauri would appear to the naked eye as a separate star from Alpha Cen A if it were bright enough to be seen without a telescope. Alpha Centauri AB and Proxima Centauri form a visual double star. Direct evidence that Proxima Centauri has an elliptical orbit typical of binary stars has yet to be found. Together, the three components make a triple star system, referred to by double-star observers as the triple star, or multiple star, Alpha Cen ABC. Together, the bright visible components of the binary star system are called Alpha Centauri AB, Alpha Cen AB. This AB designation denotes the apparent gravitational center of the main binary system relative to other companion stars. In any multiple star system, ABC refers to the orbit of Proxima around the central binary, being the distance between the center of gravity and the outlying companion. Some older references use the confusing and now discontinued designation of A times B, because the distance between the Sun and Alpha Centauri AB does not differ significantly from either star. Gravitationally, this binary system is considered as if it were one object. Astroseismic studies, chromospheric activity, and stellar rotation, gyrochronology, are all consistent with the Alpha Cen system being similar in age to, or slightly older than, the Sun, with typical ages quoted between 4.5 and 7 billion years. Gear. Astroseismic analyses that incorporate the tight observational constraints on the stellar parameters for Alpha Cen A and or B have yielded age estimates of 4.85 plus or minus 0.5 gear, 5.0 plus or minus 0.5 gear, 5.2 to 7.1 gear, 6.4 gear, and 6.52 plus or minus 0.3 gear. Age estimates for stars A and B based on chromospheric activity, calcium H and K emission, yield 4.4 to 6.5 gear, whereas gyrochronology yields 5.0 plus or minus 0.3 gear. Alpha Centauri A. Alpha Centauri A, also known as Rigil Kentaurus, is the principal member, or primary, of the binary system, being slightly larger and more luminous than the Sun. It is a solar-like main sequence star with a similar yellowish color, whose stellar classification is spectral type G2V. From the determined mutual orbital parameters, Alpha Centauri A is about 10% more massive than the Sun, with a radius about 23% larger. The projected rotational velocity, Cen I, of this star is 2.7 plus or minus 0.7 kilometers per second, resulting in an estimated rotational period of 22 days, which gives it a slightly faster rotational period than the Sun's 25 days. When considered among the individual brightest stars in the sky, excluding the Sun, Alpha Centauri A is the fourth brightest at an apparent visual magnitude of plus 0.01, being fractionally fainter than Arcturus at an apparent visual magnitude of minus 0.04. Alpha Centauri B. Alpha Centauri B is the companion star, or secondary, of the binary system, and is slightly smaller and less luminous than the Sun. It is a main sequence star of spectral type K1V, making it more an orange color than the primary star. Alpha Centauri B is about 90% the mass of the Sun and 14% smaller in radius. The projected rotational velocity, Cen I, is 1.1 plus or minus 0.8 kilometers per second, resulting in an estimated rotational period of 41 days. An earlier, 1995 estimate gave a similar rotation period of 36.8 days. although it has a lower luminosity than component A. Star B emits more energy in the X-ray band. The light curve of B varies on a short timescale, and there has been at least one observed flare. Alpha Centauri B at an apparent visual magnitude of 1.33 would be 21st in brightness, if it could be seen independently of Alpha Centauri A. Alpha Centauri C. Proxima Centauri. Alpha Centauri C, also known as Proxima Centauri, is of spectral class M6V, a small main sequence star, type 5, with emission lines. Its B-V color index is plus 1.82 and its mass is about 0.123 solar masses, m, or 129 Jupiter masses. Observation. The two Alpha Centauri A-B binary stars are too close together to be resolved by the naked eye, because the angular separation varies between 2 and 22 arcsec. But through much of the orbit, both are easily resolved in binoculars as small 5 cm. 2 in telescopes. In the southern hemisphere, Alpha Centauri forms the outer star of the pointers or the southern pointers, so called because the line through Beta Centauri, Hadar, Agena, some 4.5 degrees west, points directly to the constellation Crux, the Southern Cross. The pointers easily distinguish the true Southern Cross from the faint asterism known as the False Cross, south of about 29 degrees south latitude. Alpha Centauri is circumpolar and never sets below the horizon. Both stars, including Crux, are too far south to be visible for mid-latitude northern observers, below about 29 degrees north latitude to the equator. Roughly Hermosillo, Chihuahua City in Mexico, Galveston, Texas, Ocala, Florida and Lanzarote, the Canary Islands of Spain. During the northern summer, Alpha Centauri lies close to the southern horizon. The star culminates each year at midnight on the 24th of April at 9 p.m. on the 8th of June, as seen from Earth. Proxima Centauri is 2.2 degrees southwest from Alpha Centauri AB. This is about 4 times the angular diameter of the full moon, and almost exactly half the distance between Alpha Centauri AB and Beta Centauri. Proxima usually appears as a deep red star of an apparent visual magnitude of 11.1 in a sparsely populated star field, requiring moderately sized telescopes to see. Listed as V645 Ken in the General Catalogue of Variable Stars. G. C. V. S. Version 4.2. This UV-SETI-type flare star can unexpectedly brighten rapidly by as much as 0.6 magnitudes at visual wavelengths, then fade after only a few minutes. Some amateur and professional astronomers regularly monitor for outbursts using either optical or radio telescopes. Observational history. English explorer Robert Hughes brought Alpha Centauri to the attention of European observers in his 1592 work Tractatus de Globis, along with Canopus and Arcana, noting, "Now, therefore, there are but 3 stars of the first magnitude that I could perceive in all those parts which are never seen here in England. The first of these is that bright star in the stern of Argo which they call Canopus. The second is in the end of Eridanus. The third, Alpha Centauri, is in the right foot of the Centaur." Quote, the binary nature of Alpha Centauri AB was first recognized in December 1689 by astronomer and Jesuit priest Jean Richaud. The finding was made incidentally while observing a passing comet from his station in Puducherry. Alpha Centauri was only the second binary star system to be discovered, preceded by Alpha Crucis. By 1752, French astronomer Nicolas Louis de Lacaille made astrometric positional measurements using state-of-the-art instruments of that time. Its large proper motion was discovered by Manuel John Johnson, observing from St. Helena, who informed Thomas Henderson at the Royal Observatory, Cape of Good Hope of it. The parallax of Alpha Centauri was subsequently determined by Henderson from many exacting positional observations of the AB system between April 1832 and May 1833. He withheld his results, however, because he suspected they were too large to be true, but eventually published them in 1839 after Friedrich Wilhelm Bessel released his own accurately determined parallax for 61 Cygni in 1838. For this reason, Alpha Centauri is sometimes considered as the second star to have its distance measured because Henderson's work was not fully recognized at first. The distance of Alpha is now reckoned at 4.396 light-years or 41.59 trillion kilometers. Later, John Herschel made the first micrometrical observations in 1834. Since the early 20th century, measures have been made with photographic plates. By 1926, South African astronomer William Stephen Finson calculated the approximate orbit elements close to those now accepted for this system. All future positions are now sufficiently accurate for visual observers to determine the relative places of the stars from a binary star ephemeris. Others, like the Belgian astronomer D. Pauwbex, 2002, have regularly refined the precision of any new published orbital elements. Alpha Centauri is inside the G cloud, and the nearest known system to it is Lumen 16 at 3.6 light-years, 1.1%. Scottish astronomer Robert T. A. Innes discovered Proxima Centauri in 1915 by blinking photographic plates taken at different times during a dedicated proper motion survey. This showed the large proper motion and parallax of the star was similar in both size and direction to those of Alpha Centauri A B, suggesting immediately it was part of the system and slightly closer to Earth than Alpha Centauri A B, lying 4.24 light-years, 1.30% away. Proxima Centauri is the nearest star to the Sun. All current derived distances for the three stars are from the parallaxes obtained from the Hipparcos star catalogue, HIP, and the Hubble Space Telescope binary system, with the orbital period of 79.91 years. The A and B components of this binary star can approach each other to 11.2 astronomical units, 1.68 billion kilometers, or about the mean distance between the Sun and Saturn, and may recede as far as 35.6 astronomical units, 5.33 billion kilometers, approximately the distance from the Sun to Pluto. This is a consequence of the binary's moderate orbital eccentricity equals 0.5179 from the orbital elements. The total mass of both stars is about 2.0 m, or twice that of the Sun. The average individual stellar masses are 1.09 m and 0.90 m, respectively, though slightly higher masses have been quoted in recent years, such as 1.14 m and 0.92 m, or totaling 2.06 m. Alpha Centauri A and B have absolute magnitudes of plus 4.38 and plus 5.71, respectively. Stellar evolution theory implies both stars are slightly older than the Sun at 5 to 6 billion years, as derived by both mass and their spectral characteristics. Viewed from Earth, the apparent orbit of this binary star means that its separation and position angle, PA, are in continuous change throughout its projected orbit. Observed stellar positions in 2010 are separated by 6.74 arcsec through the PA of 245.7 degrees, reducing to 6.04 arcsec through 251.8 degrees in 2011. The closest recent approach was in February 2016. At 4.0 arcsec through 300 degrees. The observed maximum separation of these stars is about 22 arcsec, while the minimum distance is 1.7 arcsec. The widest separation occurred during February 1976, and the next will be in January 2056. In the true orbit, closest approach to Periastron was in August 1955, and next in May 2035. Furthest orbital separation at apastron last occurred in May 1995, and the next will be in 2075. The apparent distance between the two stars is rapidly decreasing, at least until 2019. Proxima Centauri. The much fainter red dwarf Proxima Centauri, or simply Proxima, is about 15,000 astronomical units away from Alpha Centauri AB. This is equivalent to 0.24 light-years or 2.3 trillion kilometers. About 5% the distance between Alpha Centauri AB and the Sun. Proxima is likely gravitationally bound to Alpha Centauri AB, orbiting it with a period between 100,000 and 500,000 years. However, it is also possible that Proxima is not gravitationally bound and thus moving along a hyperbolic trajectory with respect to Alpha Centauri AB. The main evidence for a bound orbit is that Proxima's association with Alpha Centauri AB is unlikely to be coincidental, because they share approximately the same motion through space. Theoretically, Proxima could leave the system after several million years. It is not yet certain whether Proxima and Alpha Centauri are truly gravitationally bound. In a 2017 paper, P. Curvella and F. Tevinen showed that based on new high-precision radial velocity measurements, Proxima and Alpha Centauri are in fact gravitationally bound with a high degree of confidence. The orbital period of Proxima is approximately 550,000 years, with an eccentricity of 0.50 plus or minus 0.08. Proxima comes within 4.3 plus 1.1 minus 0.9 km of Alpha Centauri AB at Periastron, and the apastron occurs at 13.0 plus 0.3 minus 0.1 km. Proxima is a red dwarf of spectral class M6VE with an absolute magnitude of plus 15.60, which is only a small fraction of the Sun's luminosity. By mass, Proxima is calculated as 0.123 plus or minus 0.06 m, rounded to 0.12 m, or about 1/8 of the Sun. Kinematics. All components of Alpha Centauri display significant proper motions against the background sky, similar to the first-magnitude stars Sirius and Arcturus. Over the centuries, this causes the apparent stellar positions to slowly change. Such motions define the high proper motion stars. These stellar motions were unknown to ancient astronomers. Most assumed that all stars were immortal and permanently fixed on the celestial sphere, as stated in the works of the philosopher Aristotle. Edmund Halley in 1718 found that some stars had significantly moved from their ancient astrometric positions. For example, the bright star Arcturus, Alpha Boo, in the constellation of Bootes showed an almost 0.5 degrees difference in 1,800 years, as did the brightest star, Sirius, in Canis Major, Alpha Cen A. Halley's positional comparison was Ptolemy's catalogue of stars contained in the Almagest, whose original data included portions from an earlier catalogue by Hippocos during the 1st century BCE. Halley's proper motions were mostly for northern stars, so the southern star Alpha Centauri was not determined until the early 19th century. Scottish-born observer Thomas Henderson in the 1830s at the Royal Observatory at the Cape of Good Hope discovered the true distance to Alpha Centauri. He soon realized this system displayed an unusually high proper motion, and therefore its observed true velocity through space should be much larger. In this case, The apparent stellar motion was found using Nicolas Louis de Lacaille's astrometric observations of 1751 to 1752. By the observed differences between the two measured positions in different epochs, using the Hipparcos star catalogue (HIP) data. The mean individual proper motions are -3,678 mass per year or -3.678 arcsec per year in right ascension and +481.84 mass per year or 0.48184 arcsec per year in declination. As proper motions are cumulative, the motion of Alpha Centauri is about 6.1 arcmin each century, and 61.3 arcmin or 1.02 degree each millennium. These motions are about 1/5 and twice, respectively, the diameter of the full moon. Using spectroscopy, the mean radial velocity has been determined to be around 20 km per second towards the solar system. As the stars of Alpha Centauri approach the solar system, the measured proper motion and trigonometric parallax slowly increase. Changes are also observed in the size of the semi-major axis of the orbital ellipse, increasing by 0.03 arcsec per century. This small effect is gradually decreasing until the star system is at its closest to Earth, and is then reversed as the distance increases again. Consequently, the observed position angles of the stars are subject to changes in the orbital elements over time, as first determined by W. H. van den Bos in 1926. Some slight differences of about 0.5% in the measured proper motions are caused by Alpha Centauri AB's orbital motion. Based on these observed proper motions and radial velocities, Alpha Centauri will continue to gradually brighten, passing just north of the southern Cross crux, before moving northwest and up towards the celestial equator and away from the galactic plane, by about 29,700 AD. In the present-day constellation of Hydra, Alpha Centauri will be 3.26 light-years or 1.00 pc away. Then it will reach the stationary radial velocity, RVL, of 0.0 km per second and the maximum apparent magnitude of -0.86 v, which is comparable to present-day magnitude of Canopus, even during the time of this nearest approach. However, the apparent magnitude of Alpha Centauri will still not surpass that of Sirius, which will brighten incrementally over the next 60,000 years, and will continue to be the brightest star as seen from Earth for the next 210,000 years. The Alpha Centauri system will then begin to move away from the solar system, showing a positive radial velocity. Because of visual perspective, about 100,000 years from now, these stars will reach a final vanishing point and slowly disappear among the countless stars of the Milky Way. Here this once bright yellow star will fall below naked eye visibility somewhere in the faint, present-day southern constellation of Telescopium. This unusual location results from the fact that Alpha Centauri's orbit around the galactic center is highly tilted with respect to the plane of the Milky Way. In about 4,000 years, the proper motion of Alpha Centauri will mean that from the point of view of Earth it will appear close enough to Beta Centauri to form an optical double star. Beta Centauri is in reality far more distant than Alpha Centauri. Planets. Proxima Centauri B. In August 2016, the European Southern Observatory announced the discovery of a planet slightly larger than the Earth orbiting Proxima Centauri. Proxima Centauri B was found using the radial velocity method, where periodic Doppler shifts of spectral lines of the host star suggest an orbiting object. From these readings, the radial velocity of the parent star relative to the Earth is varying with an amplitude of about 2 meters, 6.6 feet, per second. The planet lies in the habitable zone of Proxima Centauri. but it is possible that the planet is tidally locked to the star, resulting in temperature extremes that would be difficult for life to overcome. Alpha Centauri B. In 2012, a planet around Alpha Centauri B was announced. But in 2015 a new analysis concluded that it almost certainly does not exist and was just a spurious artifact of the data analysis. Possible detection of another planet. On the 25th of March 2015, a scientific paper by Demery and colleagues published transit results for Alpha Centauri B using the Hubble Space Telescope for a total of 40 hours. They evidenced a transit event possibly corresponding to her planetary body with a radius around 0.92 r. This planet would most likely orbit Alpha Centauri B with an orbital period of 20.4 days or less, with only a 5% chance of it having a longer orbit. The median average of the likely orbits is 12.4 days with an impact parameter of around 0 to 0.3. Its orbit would likely have an eccentricity of 0.24 or less. Like the probably spurious Alpha Centauri B. It likely has lakes of molten lava and would be far too close to Alpha Centauri B to harbor life. Possible fourth stellar object. In images taken on 7 July 2014, 343.5 GHz, and 2 May 2015, 445 GHz. Researchers discovered a source in the far infrared located within 5.5 arcseconds of Alpha Cen A, based on its proper motion. It was at first thought to be a part of the Alpha Centauri system. Further analysis, however, found that the object must be closer to the solar system, and that it may be gravitationally bound to the Sun. The researchers suggest that the object may be an extreme trans-Neptunian object, ETNO, beyond 100 astronomical units, 15 billion kilometers, a super-Earth at around 300 astronomical units, 45 billion kilometers, or a very cool brown dwarf at around 20,000 astronomical units, 3.0 trillion kilometers. Possibility of additional planets. The discovery of planets orbiting other star systems, including similar binary systems, Gamma Cephei, raises the possibility that additional planets may exist in the Alpha Centauri system. Such planets could orbit Alpha Centauri A or Alpha Centauri B individually, or be on large orbits around the binary Alpha Centauri AB, because both the principal stars are fairly similar to the Sun. For example, in age and metallicity, astronomers have been especially interested in making detailed searches for planets in the Alpha Centauri system. Several established planet hunting teams have used various radial velocity star transit methods in their searches around these two bright stars. All the observational studies have so far failed to find any evidence for brown dwarfs or gas giants. In 2009, computer simulations showed that a planet might have been able to form near the inner edge of Alpha Centauri B's habitable zone, which extends from 0.5 to 0.9 astronomical units from the star. Certain special assumptions, such as considering that Alpha Centauri A and B may have initially formed with a wider separation, and later moved closer to each other, as might be possible if they formed in a dense star cluster, would permit an accretion-friendly environment farther from the star. Bodies around A would be able to orbit at slightly farther distances due to A's stronger gravity. In addition, the lack of any brown dwarfs or gas giants in close orbits around A or B make the likelihood of terrestrial planets greater than otherwise. Theoretical studies on the detectability via radial velocity analysis have shown that a dedicated campaign of high-cadence observations with a 1-meter class telescope can reliably detect a hypothetical planet of 1.8 m in the habitable zone of B within 3 years. radial velocity measurements of Alpha Centauri B with high-accuracy radial velocity planet searcher spectrograph ruled out planets of more than 4m to the distance of the habitable zone of the star. Orbital period P equals 200 days. Current estimates place the probability of finding an Earth-like planet around Alpha Centauri A or B at roughly 85%. Although this number remains uncertain. Theoretical planets. Early computer-generated models of planetary formation predicted the existence of terrestrial planets around both Alpha Centauri A and B. But most recent numerical investigations have shown that the gravitational pull of the companion star renders the accretion of planets very difficult. Despite these difficulties, given the similarities to the Sun in spectral types, star type, age and probable stability of the orbits, it has been suggested that this stellar system could hold one of the best possibilities for harboring extraterrestrial life on a potential planet. In the Solar System, both Jupiter and Saturn were probably crucial in perturbing comets into the inner Solar System. Here, the comets provided the inner planets with their own source of water and various other ices. In the Alpha Centauri system, Proxima Centauri may have influenced the planetary disk as the Alpha Centauri system was forming, enriching the area around Alpha Centauri A and B with volatile materials. This would be discounted if, for example, Alpha Centauri B happened to have gas giants orbiting Alpha Centauri A, or conversely, Alpha Centauri A for Alpha Centauri B, or if the stars B and A themselves were able to perturb comets into each other's inner system as Jupiter and Saturn presumably have done in the Solar System. Such icy bodies probably also reside in Oort clouds of other planetary systems. When they are influenced gravitationally by either the gas giants or disruptions by passing nearby stars, many of these icy bodies then travel starwards. There is no direct evidence yet of the existence of such an Oort cloud around Alpha Centauri AB, and theoretically this may have been totally destroyed during the system's formation, to be in the star's habitable zone. Any suspected planet around Alpha Centauri A would have to be placed about 1.25 astronomical units away, about halfway between the distances of Earth's orbit and Mars's orbit in the Solar System, so as to have similar planetary temperatures and conditions for liquid water to exist. For the slightly less luminous and cooler Alpha Centauri B, the habitable zone would lie closer at about 0.7 astronomical units, 100 million kilometers, approximately the distance that Venus is from the Sun, with the goal of finding evidence of such planets. Both Proxima Centauri and Alpha Centauri AB were among the listed Tier 1 target stars for NASA's Space Interferometry mission, SIM. Detecting planets as small as 3 Earth masses or smaller within 2 astronomical units of a Tier 1 target would have been possible with this new instrument. The SIM mission, however, was cancelled due to financial issues in 2010. View from this system. Viewed from near the Alpha Centauri system, the sky would appear very much as it does for an observer on Earth, except that Centaurus would be missing its brightest star. The Sun would be a yellow star of an apparent visual magnitude of plus 0.5 in eastern Cassiopeia, at the antipodal point of Alpha Centauri's current right ascension and declination. At 02H 39 meters 35 plus 60 degrees 50. 2000. This places close to the 3.4 magnitude star Epsilon Cassiopeia. Because of the placement of the Sun, an interstellar or alien observer would find the of Cassiopeia had become a shape nearly in front of the Heart Nebula in Cassiopeia. Sirius lies less than a degree from Betelgeuse in the otherwise unmodified Orion, and with a magnitude of minus 1.2 is a little fainter than from Earth but still the brightest star in the Alpha Centauri sky. Procyon is also displaced into the middle of Gemini, outshining Pollux, whereas both Vega and Altair are shifted northwestward relative to Deneb, which barely moves, due to its great distance, giving the summer triangle a more equilateral appearance. View from Proxima Centauri B. From Proxima Centauri B, Alpha Centauri A B would appear like two close bright stars with the combined apparent magnitude of -6.8, depending on the binary's orbital position. The bright stars would appear noticeably divisible to the naked eye, or occasionally, but briefly, as a single unresolved star, based on the calculated absolute magnitudes. The visual apparent magnitudes of Alpha Centauri A and B would be -6.5 and -5.2, respectively. View from a hypothetical A or B planet. An observer on a hypothetical planet orbiting around either Alpha Centauri A or Alpha Centauri B would see the other star of the binary system as an intensely bright object in the night sky, showing a small but discernible disk while near periapse. A up to 210 arcseconds, B up to 155 arcseconds. Near apoapse, the disk would shrink to 60 arcseconds for A, 43 arcseconds for B, being too small to resolve by naked eye. In any case, the dazzling surface brightness could make the disks harder to resolve than a similarly sized, less bright object. For example, some theoretical planet orbiting about 1.25 astronomical units from Alpha Centauri A, so that the star appears roughly as bright as the Sun viewed from the Earth, would see Alpha Centauri B orbit the entire sky once roughly every 1 year and 3 months, or 1.34 A, the planet's own orbital period. Added to this would be the changing apparent position of Alpha Centauri B during its long, 80-year elliptical orbit with respect to Alpha Centauri A. The average speed, at 4.5 degrees per Earth year, is comparable in speed to Uranus here, with the eccentricity of the orbit. The maximum speed near periapse, about 18 degrees per Earth year, is faster than Saturn, but slower than Jupiter. The minimum speed near apoapse, about 1.8 degrees per Earth year, is slower than Neptune, depending on its and planet's position on the respective orbits. Alpha Centauri B would vary in apparent magnitude between -18.2, dimmest, and -21.0, brightest. These visual apparent magnitudes are much dimmer than the apparent magnitude of the Sun as viewed from the Earth, -26.7. The difference of 5.7 to 8.6 magnitudes means Alpha Centauri B would appear, on a linear scale, 2,500 to 190 times dimmer than Alpha Centauri A, or the Sun viewed from the Earth, but also 190 to 2,500 times brighter than the full Moon as seen from the Earth, -12.5. Also, if another similar planet orbited at 0.71 astronomical units from Alpha Centauri B, so that in turn Alpha Centauri B appeared as bright as the Sun seen from the Earth, this hypothetical planet would receive slightly more light from the more luminous Alpha Centauri A, which would shine 4.7 to 7.3 magnitudes dimmer than Alpha Centauri B, or the Sun seen from the Earth, ranging in apparent magnitude between -19.4, dimmest, and -22.1, brightest. Thus Alpha Centauri A would appear between 830 and 70 times dimmer than the Sun but some 580 to 6,900 times brighter than the full Moon, during such planet's orbital period of 0.63 A. An observer on the planet would see this intensely bright companion star circle the sky just as humans see with the solar system's planets. Furthermore, Alpha Centauri A's sidereal period of approximately 80 years means that this star would move through the local ecliptic as slowly as Uranus with its 84-year period. But as the orbit of Alpha Centauri A is more elliptical, its apparent magnitude will be far more variable. Although intensely bright to the eye, the overall illumination would not significantly affect climate nor influence normal plant photosynthesis. An observer on the hypothetical planet would notice a change in orientation to very long baseline interferometry reference points commensurate with the binary orbit periodicity plus or minus any local effects such as precession and nutation. Assuming this hypothetical planet had a low orbital inclination with respect to the mutual orbit of Alpha Centauri A and B, then the secondary star would start beside the primary at stellar conjunction. Half the period later, at stellar opposition, both stars would be opposite each other in the sky. As a net result, both the local Sun and the other star would each be in sky for half a day. Like Sun and Moon are both above horizon for half a day. But during stellar conjunction, the other star being new would be in sky in daytime, while during the opposition, the other star being full would be in sky for the whole night. In an Earth-like atmosphere, the light of the other star would be appreciably scattered, causing the sky to be perceptibly blue though darker than in daytime. Like during twilight, a total solar eclipse, humans could easily walk around and clearly see the surrounding terrain, and reading a book would be quite possible without any artificial light. Over the following half period, the secondary star would be in sky for a progressively decreasing part of night and increasing part of day, until at the next conjunction the secondary star would only be in sky in daytime near the primary star. From a planet orbiting Alpha Centauri A or B, Proxima Centauri would appear as a 4th to 5th magnitude star, as bright as the faint stars of the Little Dipper. Other names in modern literature: Rigil Kent, also Rigil Kent in variants Rigil Knt, and Ptolemy, were cited as colloquial alternative names of Alpha Centauri. Rigil Kent is short for Rigil Kentaurus, which is sometimes further abbreviated to Rigil or Rigil, though that is ambiguous with Beta Orionis, which is also called Rigil. Although the short form Rigil Kent is often cited as an alternative name, the star system is most widely referred to by its Bayer designation Alpha Centauri. The name Ptolemy originates with Jacobus Golius's edition of Alphagones Compendium, published posthumously in 1669. Ptolemy is Golius's Latinization of the Arabic name Al-Ulman, the ostriches, the name of an asterism of which Alpha Centauri formed the main star. During the 19th century, the northern amateur popularist Elijah H. Burritt used the now obscure name Bungula, possibly coined from beta and the Latin ungula, hoof. Together, Alpha and Beta Centauri form the southern pointers, or the pointers, as they point towards the Southern Cross, the asterism of the constellation of Crux. In Standard Mandarin Chinese, Nan Mia Qten, meaning Southern Gate, refers to an asterism consisting of Alpha Centauri and Epsilon Centauri. Consequently, Alpha Centauri itself is known as Nan Mia Qten, the second star of the Southern Gate. To the Australian Aboriginal Burong people of northwestern Victoria, Alpha and Beta Centauri are Burmbungal, two brothers noted for their courage and destructiveness, who speared and killed Chingal, the emu. The Coalsack Nebula, the form in Woot Jobaluk is Brambult. Exploration. Alpha Centauri is envisioned as a likely first target for manned or unmanned interstellar exploration, crossing the huge distance between the Sun and Alpha Centauri using current spacecraft technologies would take several millennia, though the possibility of nuclear pulse propulsion or laser light sail technology, as considered in the Breakthrough Starshot program, could reduce the journey time to a matter of decades. Breakthrough Starshot is a proof-of-concept initiative to send a fleet of ultra-fast light-driven nanocraft to explore the Alpha Centauri system, which could pave the way for a first launch within the next generation. An objective of the mission would be to make a flyby of, and possibly photograph, any planets that might exist in the system. Proxima Centauri B, announced by the European Southern Observatory (ESO) in August 2016, would be a target for the Starshot program. In January 2017, Breakthrough Initiatives and the ESO entered a collaboration to enable and implement a search for habitable planets in the Alpha Centauri system. The agreement involves Breakthrough Initiatives providing funding for an upgrade to the VISIR, VLT imager and spectrometer for mid-infrared instrument on ESO's Very Large Telescope, VLT, in Chile. This upgrade will greatly increase the likelihood of planet detection in the system. Distance. See also Alpha Centauri in fiction. List of nearest stars and brown dwarfs. Project Longshot. Notes. SIMBAD Observational Data. 6th Catalogue of Orbits of Visual Binary Stars U. S. N. O. The Imperial Star, Alpha Centauri. Alpha Centauri, A Voyage to Alpha Centauri. Immediate History of Alpha Centauri. ESCI. Alpha Centauri. Alpha Centauri at Constellation Guide. Hypothetical Planets or Exploration. A Family Portrait of the Alpha Centauri System. Spacerf.com. Retrieved 21 March 2003. Alpha Centauri System. O Sistema Alpha Centauri. Portuguese. Alpha Centauri. Associação de Astronomia. Portuguese. Thompson, Andrea. 7 March 2008. Nearest star system might harbor Earth twin. Space.com. Archived from the original on 2 June 2008. Retrieved 17 July 2008.